I want to talk just selected solutions to some of the problems on the homework, because I want to save the class time to doing poker hand stuff, which is challenging but good exercises. So here's one. I think I started you guys with this one. Remember, the numbers are one off from the version you have, but I want to go back to this one, which I probably should have done first. How many lines are determined by 6 points, no 3 of which are collinear? So for example, if I draw a hexagon, then there's not any 3 points on this that are in a line, so that satisfies that. And that is going to relate to number 16. And so how many lines are determined by those guys? Well, you could just draw it because it's not that many, but we want to think about this as, can we relate it to standard counting problems? And the key thing is the relationship between points and lines. When I see the words lines, determined, and points, what I think of is the fact that 2 points determine a line, that there's a one line between any 2 points. Okay, suddenly that makes it into a standard counting problem, because for any 2 points in among my set of 6, I can connect them. Let's see. I can connect them with a line. So I could connect this one with this one, or this one with this one, or this one. I could draw all of these. I'm not going to draw all of them right now, but I could draw this lines from this point to any of the other points. Now I happen to have the hexagon, the outer edge of the hexagon, already drawn. So for any one of these points, I can draw a line to any of the other ones. Or in other words, for any pair of points, that's going to give me a line. And the no 3 of which are collinear means that if I take 2 points here, that determines a line. Or 2 points here, they're going to be a different line. And so I'm not accidentally going to get the same line twice. So what that means is that I'm going to have, instead of thinking about the lines directly, I could think about the points and think of them as choosing pairs of points. And so that's not an obvious thing. It makes it it's a challenging problem. But it's a wonderful example of changing your mindset and turning something into a standard counting problem. Instead of counting lines, we're counting pairs of points. So let's see. Can I choose the same point twice? No. So it's without replacement. And does order matter? Well, if I choose this point and then this point, that determines this line. If I choose this point and then this point, it's the same thing. So that's going to be 6, C, 2. No replacement, without order, and that is 15. So what about how many diagonals does a regular hexagon have? Well, there's a couple ways to do this. One would be you go off of this problem, which of course I didn't have you do, which I probably should have had you do. Knowing this number, it's quite easy to do number 16, because this gives us all of the segments between the vertices of the hexagon. It's going to look kind of crappy because paint isn't the best way to do this, but oh well. It's what I have. Let's see. I think I still need this guy and this guy. The 15 lines are going to be all of the ways I can connect any 2 pairs of points, and then I want diagonals. Oh, they can be non-adjacent vertices. Oh, well, I know how many outer segments there are. That's 6. And so it's just going to be, this is an example of the subtraction counting principle. Count something that's purposely more than you want, and then throw out the cases that you don't want. This is different from systematic overcounting and division. I didn't group them and then divide. That's what happened here, basically, is I took 6 times 5. I could have taken 6 times 5 pairs of points and then divided by 2 because it was overcounting. But here I'm counting stuff and purposely counting stuff that's just wrong, that I don't want, and I subtract it to get it out. So that's one way. Or the other way to do it is go back to basic counting principles again. For each point, for each vertex of the hexagon, there are 3 other points that are connected by diagonals, because I can't connect it to itself or to its 2 neighbors around the edge. So that means we have 6 points for where we start the line. There are 3 choices of where to go to, but then wait a minute, I counted this with order, and order doesn't matter. Another way to say it is, like this diagonal, I counted it as going from this point to this point. But then as I walk around, I also accidentally overcounted it. I said, oh, it's also going from this point to this point. That's the same thing. But luckily, it was systematic overcounting, because every line, every segment is going to get counted twice there. And so that's again going to mean 9. Either way, they're both very good ways and good examples of our basic counting principles of choice problems, subtraction, systematic overcounting, and division. Okay. So the other one, let's see, another one that's a good one. Oh yeah, this one. Let me just make the hint more explicit here. What we can do is, one way to do this is line up all the students. Don't let them move. Just line up all the students. And then they say, okay, we're going to make up 15 cards that say section A, 15 cards that say section B, 15 cards that say section C, and 15 cards that say section D. So in other words, we're making a word with 15 A's, 15 B's, 15 C's, and 15 D's. And I don't want to write all 15. Okay, it's going to be a 60-letter word. 60 letters total. Okay. And then we just shuffle them all up. We shuffle them all to get all in some random order, and then hand them out one by one to the students who are waiting in line. That's going to be a way to put all of the students into the sections. And you might think, oh, that's going to be 60 factorial. But it doesn't matter if I switch any two A's with each other, or switch any two B's with each other, or C's or D's. And so that's exactly just how many genuinely different anagrams or distinguishable permutations of these guys are going to be. And so it's going to be 60 factorial over 15 factorial times itself 4 times, or in other words, that's just that to the 4th power. So that's how many total letters there are. That's how many groups. There's 4 groups of 15 letters each. And that turns out to be this pretty big number. 10 to the 33. That is a very, very large number if you just kind of did this randomly. Okay. So that's, if I hadn't given any hint, I think it's a fairly hard problem. I think people have a hard time starting this. With the hint, I was hoping that people would have more of a start on it, but I think it's still challenging. And these, I'm hoping these ones are more straightforward. And these ones are straightforward. Here, if I've got 16 students, and I'm looking at 16 choose, this is going to be 16 choose n. And the question is, when is that biggest? Well, remember, what pattern do those numbers make? That's the 16th row of Pascal's triangle. That's the 16th row of Pascal. And we know that the numbers for Pascal are biggest in the middle. And so we're going to get biggest is 16C8. And so that's an important thing to realize, is that the choose numbers get biggest not when this number is big or when it's small. It's when this number is in the middle. That's quite different from 21, where you discover that the bigger this number is, if I'm lining people up in order, then the most possibilities is going to be when I line them all up, and it's going to be more the more I line up. That's not true with combinations. If I line up people, if I just take a group out without order, then if I don't choose anybody, 16C0 is just 1. There's no one way to do that. But if I choose everybody, there's only one way to do that as well. And it's biggest actually in the middle when I choose exactly half of the people. I'll stop there.